Okay, welcome back, students. We're going to do 3.3 to 3.5 today. Finish up chapter 3. More probability. Go ahead and share my screen. Okay, so we have the addition rule to go over today. Okay, so the probability of A union B, or A or B, remember those Venn diagrams that we went over. We'll look at them again as well. But the probability of A union B is probability of A plus the probability of B minus the overlap. Okay, this is probability of A intersection B, that's the overlap. And we do not want to count that overlap twice. Okay. If A and B are disjoint, let me write that a little bit better. Overlap. It's hard to write on the screen. Okay. So if they are disjoint, means that they have no overlap. Then it's just probability of A plus probability of B. Let's look at the Venn diagrams on these. Okay, if there is overlap, and it looks like this, we have A and B. Okay, and then we want to know, okay, so if I do the probability of A, let's do that in light blue here. So probability of A, we would get that. That's the probability of A. If we did the probability of B, let's do that in green, we would get this. And notice what area I ended up counting twice. I ended up counting the overlap, A intersection B. I ended up counting that twice. So I don't want to count it twice, so I subtract off one of them. Okay. Okay, if they're disjoint, then we don't have to worry about the overlap. We just do the probability of A, probability of B, and that's the union of A and B. Okay, it's just the probability of A plus the probability of B. We don't have to worry about that overlap. Okay, okay, example 1, pre-employment drug screening results of 1,000 employees. We have those who those subjects who use drugs. Positive test result is 44 here. Negative test result is 6. Okay, so this is a false negative. Okay, subject is not a drug user. We had 90 false positives, but we had 860 true negatives. It just means that this test is not 100%. Okay, it means that you can get false negatives and false positives. Okay, notice that we only have 50 people here. Okay, but we have 950 people here. Okay, so we only had 50 drug users, 6 of which got away scot-free here of not having, the repercussions of the drug test showing that they were a drug user. Okay, 44 of the 50, it showed that they were true drug users. Okay, of the 950 employees, 860 had a true negative result, but 90 of these guys had a false positive. Those guys I'm actually more concerned about, because they're being falsely accused of a crime they didn't commit. Okay, so no test is 100% complete accurate. So these guys the 90 there would obviously want to retest. If one subject is randomly selected from 1,000 subjects, okay, given a drug test, find the probability of selecting a subject who had a positive test result. Okay, so how many of these people had a positive test result? 90 plus 44 is 134. Okay. Okay. So find the probability of selecting a subject who had a positive test result or uses drugs. Okay, so probability of a positive test result or probability of them using drugs. Okay, so what we're going to do here is we're going to use that formula that we talked about. Okay, probability of A union B is the probability of A plus the probability of B minus the probability of A intersection B. Okay, the overlap here. Okay, so we're going to say that this is the probability. A is that they had a positive test result. Okay, I'm just going to put a positive symbol there to represent positive test result. A probability of B is that they actually use drugs. Okay, so I'll just put uses there. Okay, minus the probability that they had a positive result and they use drugs. Okay, and uses, positive and uses. Okay, so what's the probability that they tested positive? Okay, well, that's the 134 there. So that's 134 out of 1,000. What's the probability that they use drugs? Well, that's 50 people out of 1,000. Minus the probability that they use and they're positive. These are our true positives. Okay, that's that 44 right there. Okay, those are our true positives. So we're going to subtract off the 44. Okay, so if I take 134 plus 50, that's going to give me 184. Okay, minus 44 is going to give me 140. So this ends up being 140 out of 1,000. If I reduce that, plug that into my calculator, I get 140 divided by 1,000, which is 0.14 or 14%. Okay, so there's a 14% chance that the person either tests positive or is a drug user. Okay, let's do another example. Okay, 35% of all homeowners in a large town hire someone to maintain their yard. 12% of the homeowners hire someone to clean their home. 9% of the homeowners hire someone to maintain both their yard and their home. What is the probability of randomly selecting a homeowner who hires someone to maintain their yard or clean their home? Okay, so probability of yard unioned with home. Okay, probability of yard union home. Okay, yard or home is equal to the probability of yard, okay, plus the probability of home minus one of the overlaps. Okay, probability of yard is going to include the yard and home. The probability of home is going to include the yard and home. So we just have to subtract off one of the overlaps, which is the probability of yard and home, or intersection home. Okay, so in this union, you can think of as an or statement. This intersection, you can think of as an and statement. At the end, by the way. Okay, so what's the probability of yard and or home? That's the probability of yard, so that would be 35% or 0.35, plus the probability of home, which is 0.12, 12%, minus the probability of both yard and home. Those are the rich people. Okay, so 35, 0.35 plus 0.12 plus 0.9. Okay, so 35 plus 12 is 47, minus 9 is 38. So this is 0.38 or 38%. Okay. What is the probability of randomly selecting a homeowner who neither hires someone to maintain their yard nor clean their home? So 38% of them either. This or means either. So if I know that 38% either have a gardener, I'll say gardener, or housekeeper. Okay, if 38% either have either a gardener or a housekeeper, then how many don't? Well, that's 1 minus 0.38, which is 0.62. That's the complement that we talked about before. So 62% have neither. Okay. Okay, here we have a deck of playing cards. Okay, so this is the sample space. We call this a sample space for playing cards. There's 52 cards, 4 sets, okay, 13 cards in each, 4 suits, 13 cards in each suit. Okay. So what is the probability of randomly choosing a heart or a queen? Okay, so the probability of a heart or a queen is equal to the probability of getting a heart plus the probability of getting a queen minus the probability of getting the queen of hearts. Okay, so what does this look like? Well, let's pull out the highlighter here. If I have the hearts, which one are the hearts? Yeah, it's these guys. If I have the queens, okay, that's these guys here. Those are the queens. And so which one gets counted twice? Well, it's the queen, it's this guy right here, the queen of hearts. Okay, that guy there gets counted twice. I don't want to count it twice. I just want to count it once. What's the probability of getting a heart? Well, how many hearts are there? There are 13 hearts. Ace through king is 13. So this is 13 out of 52. Okay, plus how many queens are there? There are 4 queens, 4 out of 52, minus that one queen of hearts that ends up being in both categories. So 13 plus 4 is 17, minus 1 is 16. So this is 16 out of 52. I can divide both top and bottom by 4, and I get 4 out of 13. Okay. And you can change it to a decimal. It's not a pretty decimal, but if you want to change it to a decimal and round, you can. I'm going to leave it as 4 over 13. Okay. Okay, what's the probability of randomly selecting a face card or an ace? Okay, a face card are the ones that have faces on them. Okay, those are the jack, kings, and queens. Okay, and ace is just the one card. Okay, has an A for ace. Okay, so what's the probability? The probability of getting a face card or an ace is equal to the probability of getting a face card, face card, plus the probability of getting an ace minus the overlap, face and ace, right? Okay, so how many face cards are there? Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 face cards. So that's 12 out of 52. How many aces are there? There's 1, 2, 3, 4. There's 4 aces. And how many face cards and aces are there? Well, there's none. Okay, there's none. You can't be a face card or an ace at the same time. You have to choose. Okay, so we say that those are mutually exclusive. Okay, because there's 0. Okay, face and ace are mutually exclusive. Okay, it can't happen. So this goes back to that Venn diagram where we had the faces and the aces, right? So this is face, this is ace, and they're mutually exclusive. So all we do is we just add here, and again we get 16 over 52, or 13, or 4 out of 13. So this is 16 over 52, or 4 out of 13 again. Okay, employment data at a large company, example 4, revealed that 72% of workers are married, that 40% are college graduates, and half of the college graduates are married. Okay, so 50%, that's what half means. 50% of the college graduates are married. Okay. Okay, 50% of the college graduates are married. Okay, so what's the probability that somebody's married or a college graduate? Okay, so let's look at the Venn diagram real quick. Otherwise, it's going to get kind of confusing. Okay, the probability that you are married is 72%, 0.72. Okay, the probability that you are a college graduate is 0.44. Okay, so is 0.72, but if you're a college graduate, that's 0.44, right? But what's the overlap here? Well, you can be married and a college graduate, and it says 50% of the college grads. Well, what percentage is the college grads? That's 44%. So 22% are actually the college graduates, because that's 50%, 0.5 times 0.44 is 0.22. That's half of the entire population of college graduates are married. And so that's if the entire probability that you are a college graduate is 44%, then half of that is 22%. Okay, so I'm going to have to erase these. Okay, and I'm going to say, okay, I know the intersection is 22%. Let me draw my diagram a little bit bigger. Okay, I know my intersection is 22%. Okay, so let me zoom in. 0.22. Okay, I know that it's 22%. Because half of the college graduates are married, but half of them are not. Okay, so 0.22 are married and 0.22 are not married. Okay, so these are the college graduates. But what about my married workers? Okay, well, the marrieds, 72% are married, but that includes the 22% that are college graduates. So how many are married but not college graduates? Yeah, we just subtract the 22 from the 72, and that's 50%. Okay, so that was 0.72 minus 0.22. Okay, let me put that down here. 0.72 minus 0.22. Okay, so using the Venn diagram, we can actually calculate the married or college graduate by just adding up the 0.50, the 0.22, and the 0.22 here. Okay, we don't have to subtract off the overlap because we already did. We already subtracted off the overlap when we took it away from this 0.72. Okay, we subtracted one already. So the probability of married or college is going to be 0.50 plus 0.22 plus 0.22. This is the probability that you're only married. This is the probability that you're only college. And this is the probability that you're both. We're going to add that up, and we would end up with 0.94. Okay, or 94% of them are married or went to college. So there's only 6% that did not get married or go to college. Okay, so I guess that's the next problem here is what's the probability of neither, okay, neither, we'll say not married or college. And that's a 1 minus that 0.94, which is 0.06. So that's the probability that you're either not married or you didn't go to college. Okay, a real estate ad suggests that 64% of homes for sale have garages. 21% have swimming. I guess that would be swimming pools. There we go. Okay, swimming pools, and 17 have both features. Okay. What's the probability that it has a pool or garage? Okay, so same type of problem. We're just going to use the, we're not going to do a Venn diagram on this. We're just going to use the formula. So probability of pool, or sorry, garage, probability of garage or pool is equal to the probability of garage minus plus the probability of pool minus the probability of both, minus the probability of pool and garage. Gosh, I keep doing this backwards. Garage and pool. Okay, so probability of garage is 0.64. Probability of pool is 0.21 minus the probability that they have both, which is 0.17. So let's go to our calculator on this. 0.64 plus 0.21 minus 0.17 is 0.68. So 68% have a pool or a garage. Which ones have neither? Well, that's just 1 minus 0.68, which is 0.32. Okay, so that's what we call the addition rule. Okay. Let's get into the multiplicative rule, or conditional probabilities. Okay. Okay. A conditional probability notation. This is the probability of B given that A already occurred. Okay. This is the meaning is, what is the probability of B given that we know A has already occurred? It already occurred. Okay. It already happened. Okay, think conditional because it's based on the condition that A has already occurred. Okay, so we have a formula here. The conditional probability formula is that we take the probability of A and B and divide it by the probability of A. Okay, draw a Venn diagram to see why this works. Remember what we want over what is possible, or the desired over the possible, right? So the desired over the possible is the probability. Okay, so here's the thing is we want what's the probability of B given that A has already happened. Okay, so let's look at the Venn diagram on this one. Okay, so we know that A has already happened. A has already happened. Okay, so we know that, you know, we're just looking at, say, the people with funny hats. Okay, so if A is funny hats, we already know that they have a funny hat. Okay, but if B is blue eyes, then we want to know what's the probability of blue eyes given that they already have a funny hat. Okay, so B. Okay, so what we want to do is we want to exclude anything that is not in A. We want to exclude anything that is not an A here. So we want to get rid of all of this stuff. Okay, we want to exclude anything that's not an A. Okay, so what we're really looking at here, probability of B given that A already occurs, we want to get rid of this stuff. And then focus only on the highlighted portion here. We want to focus on just that. So basically what we're doing is we're saying, look, we're only looking in A. Only look in A. Basically, here's your Venn diagram. We only look in A, and we only care about the probability of the B portion, right, in A. So this is B in A. So B in A. We only care about this portion of B that's in A. So what's the probability of B given A? Is the intersection over A, because we only care about A. We don't, okay, we don't care about the probability of B occurring without A, because we're saying that A happens first. Okay, we've already selected the funny hat people, and now we want to know the blue-eyed people inside the funny hat people. We don't care about the blue-eyed people that aren't wearing funny hats. Okay, so we're getting rid of not A, all the not A. Okay, we're getting rid, it has to be in A. Okay, suppose we roll a 6-sided dice. Okay, find the probability of rolling a 5. Okay, given that we roll a number greater than 3. Okay, so let's look at this. These are kind of two different problems. I don't know why they counterimpose these on each other. But suppose we roll a 6-sided dice once. Find the probability that of oh, I see what they're doing here. They just want to do extra ones down there. But let's do this first one first. Probability roll a 5 given that we've already know that it's a roll greater than 3. So in our sample space 1, 2, 3, 4, 5, 6, what this is saying is, look, we already know that it's going to be a 4, 5, or 6. We already know that it has to be a number greater than 3. Okay, so instead of rolling a 5 is 1 out of 6, now it's 1 out of 3. Okay, it's 1 out of 3. So if we were to use the formula, we could use the formula there. So this is 1 out of 3 now. We could have used the formula that says, what's the intersection of A and B? What's the intersection of rolling a 5 and being greater than 3? Well, that's 100%. Sorry. What's the intersection of rolling a 5 and rolling a number greater than 3? Well, again, yeah, that's 100%. Okay. Over the probability, let me think about this for a second. Yeah, so the probability of rolling a 5 is 1 out of 6. Okay, so probability of rolling 5 is 1 out of 6. Then the probability of rolling a number greater than 3 is 3 out of 6, right? And so if I reduce this, I get 1 out of 3. Okay. If I use this is the probability of rolling, probability of a 5 over the probability of greater than 3. Okay, is equal to 1 out of 3. Okay, so let's say we draw a single card at random. What's the probability of getting a heart? Well, that's 1 out of 4. There's only 4 suits. It's 1 out of 4. What's the probability of getting a heart, knowing that I already have a red card? Well, there's only 2 red suits. Okay, so it would be that ends up making it half as much. So it's 1/2. Okay. Probability of let me make sure that we understand. How many hearts are there? There are 13 hearts out of 52 cards, which is 1 out of 4. How many hearts are there? There's 13 cards, but now because we know that it's a red, how many red cards are there? Well, there are 26 reds, which is 1/2. Okay, what's the probability of a card being red? Well, it's going to be half. It's going to be 26 out of 52. 1/2. What's the probability of a card being red, given that I already know it's a heart? Well, it's 100%. You can't have a heart that's not a red. So this is 13 cards are red out of 13 red hearts out of 13 hearts, right? Red and heart out of 13 red hearts. So that's 1. Okay, 100%. Probability of being a king is 4 out of 52, which is 1 out of 13. And the probability of being the king of hearts, okay, probability of being king of hearts, that's 1 out of 52. Okay, and the probability of being a heart is 1 out of 4, or 13 out of 52. And so we can cancel the 52s, and that becomes 1 out of 13. Okay, you recently interviewed for a job as Statistical Awesomeness Corporation. As a statistician, you look at the previously collected data and estimate there is a 50% chance that the company will call you back and that they will offer you the job. From your experience, you estimate there's an 80% probability that they will call you back whether you got the job or not. Okay. Suppose the phone rings and the number on the caller ID is from SAC. What is the probability that you will be offered the job? Okay, what's the probability that you get the job and a callback? Okay, well, that's 50%. What's the probability of just getting a callback? Well, it's 80%. Okay, so this is going to be 0.5 over 0.8, or 0.50 over 0.80. Is 0.625, okay, or 62.5%. Okay, 0.625 or 62.5%. Okay, that's a probability that they give you the job, okay, given that they call you back. Okay, 80% of the time they're going to call you back. 20% of the time you're not going to get a call. Okay, so 80% of the time you will get a call. 62.5% of the time you'll get a call and you'll get the job. Okay. If two events are independent, okay, then the probability of B given A is just the probability of B. Okay, if we look at the Venn diagram, okay, probability of B given A is equal to probability of B. Okay. Excuse me. Okay, so if we look at the Venn diagram real quick, okay, if they are independent events, okay, probability of B given A is just equal to the probability of B. Okay, so here's A, here's B, right? So A already occurred, okay, but does that affect B? No. No. Just because A already occurred doesn't affect the probability of B, so the probability of B is still the same. Okay. Okay, so the alternative way of thinking this, okay, is the probability of A and B occurring is equal to the probability of A occurring times the probability of B occurring. Okay, and it says come back we'll come back to alternative definition. I'll show you how to derive that in a minute. Okay. Okay. Okay, so let's flip a coin twice in successive trials. The probability of A is first flip is heads, that's 1/2. Probability of B, second flip is heads, that's also 1/2. Probability of B, B given A, okay, is the probability of A, or sorry, it's just the probability of B. This is the probability of B. okay, which is just 1/2. It didn't matter that the first flip was heads. That probability of B doesn't matter. The first flip could have been tails, and since the trials are independent of each other, one does not affect the other, then probability of B occurring is still 1/2. It didn't matter that A has already occurred. Okay, it's still 1/2. Suppose we roll a die, then we flip a coin. Probability of rolling a 1 and flipping heads. A is probability of rolling 1. Well, that's 1/6. Okay. What's the probability of getting A given that B occurred? Well, that's just the probability of A. It doesn't matter. Again, these are two mutually exclusive events. They don't affect each other. So this is just going to be probability of A, which is 1/6. Okay, probability of B, flipping a head, that's 1/2. Okay, probability of B given A, well, that's just going to be probability of B again, which is 1/2. Okay. Okay, suppose we draw a single card out of a standard 52 deck. Okay. Probability of A is drawing a heart. Okay, so we're going to draw a heart. Well, how many hearts are there? There are 13 hearts out of 52, right, which is 1/4. Okay, probability of A given B. Okay, probability of A given B. Well, this is going to be the probability of A and B over the probability, and we want to draw a king. Well, is there a king of hearts? We know that these are not independent if there's overlap. And yes, there is a king of hearts. So probability of A and B over the probability of B, okay? Okay, so what's the probability of getting a king of hearts? Well, that's 1 out of 52. What's the probability of getting a king? Well, there's 4 of those. Okay, there's 4 of those out of 52. And so when we cancel the 52s, we get 1 out of 4. Okay. Okay, concentration label, 1 milligram is 1 mm solution, or 1 milligram in 1 mm solution. Ratio, 1 milliliter of a 1 in a 1,000 solution. Okay. So let's see if we can navigate this concentration label and ratio label. Okay. So on the concentration label, the correct dosage is 11, the wrong dosage is 3. Okay. On the ratio label, the correct dosage is 2, the wrong dosage is 12. Okay, so what's the probability of getting a correct dosage? Okay, well, we have to kind of add these up. This is going to be, the probability of getting a correct dosage here is 13. Okay, out of, okay, probability of getting just a dosage. Well, how many dosages are there? I have to add these up. This is going to be 11 plus 3 plus 2 plus 12. So 13 in one column, 15 in the next column makes it 28 total, dosages. Okay, so 13 correct dosages. Okay, out of 28 total dosages. What's the probability of a correct dosage given that it's only the ratio label? Given that we know it's the ratio label already. So this is where we can say, okay, we're just going to isolate the ratio label. Well, instead of 13 out of 28, it's now 2 out of 14 because we only look at ratio. We isolate. Whatever that given is the isolation. We isolate the given. Okay, correct dosage given that it's the ratio label, and that's going to be 2 out of 14. So this is 2 out of 14. Okay. Are dosage correctness and label type independent of each other? Okay, meaning that does the probability of B given A equal the probability of of B? Okay, if they were independent, then that would be true, right? The probability of the correct dosage would be equal to the probability of the correct dosage regardless of which label. Okay, regardless of which label. And is that correct? Well, no, these two are not the same. So the probability of a correct dosage, okay, is 13, so PB is 13 out of 28. The probability of a correct dosage given the ratio label is 2 out of 14, and they are not equal. 13 out of 28 does not equal 2 out of 14, so they are not independent. Does knowing the ratio label increase or decrease the probability of correctness? Okay. It decreases. Okay. No, dependence does not necessarily signify cause-effect relationship. Okay. Just because things are dependent doesn't mean that they cause each other. Okay. One does not necessarily cause the other. Having funny hats does not necessarily cause you to have blue eyes. Okay. Just because one might be in relation to each other doesn't cause it. Okay. Okay. So the way that we would see that this decreases, maybe it's harder to see, is that if we doubled this, I would get 4 out of 28, right? So just knowing the correct dosage, we get 13 out of 28, right? But going to the ratio label, we end up with 4 out of 28 for the correct dosage. So that was a decrease, right? It went from 13 to 4. Okay, that's why it decreases. So it might be hard to compare. That's the word I was looking for. Compare the two fractions. Might be hard to compare the two fractions without having a common denominator. So if you can make that common denominator, and you say, oh yeah, it was a 13, having all of the data, and then it went to 4, just isolating that ratio label. Okay. Okay, let's look at the multiplication rule here. Okay, and this rule can be derived from the conditional probability rule. Okay, so remember when we had, if they were independent, if independent, okay, we said that the probability of B given A, okay, or sorry, the probability of A and B, the probability of A and B, we need to go back to first grade and learn how to write. If independent, then the probability of A and B is equal to the probability of A times the probability of B. Okay, and we said that, this was true based on this formula. Okay, now, how can we get that? Well, we get it from the fact that the probability of B given A is equal to the probability of A and B all over the probability of A. Okay. But if they were independent, then what was the probability of B given A? The probability of B given A was B. Okay, this equals the probability of B, if independent, right? And so what can we do? We can multiply both sides by the probability of A. Okay, and so this becomes the formula that we were looking for. Probability of A times the probability of B is equal to the probability of A and B. That's if they're independent, okay? Now, if they're not independent, then this probability of A, probability of B given A, you can't make it probability of B, okay? But you just leave it. You just leave it like this, okay, on this side. So that's where this formula comes from, okay? We just multiply both sides by probability of A, okay? And we get that formula. If they're independent, then this probability of B given A turns into just probability of A, probability of B, sorry. Okay. So let me maybe write this a little less confusing. Okay, let's say that they're not independent. And so we get the probability of B given A is equal to the probability of A and B over the probability of A. And so what do we want to do? We just want to multiply both sides by probability of A. Okay, and we get probability of A given B. A and B is equal to the probability of A times the probability of B given A. Okay, what's the probability? And then again, we said that this thing, if they're independent, this thing was the probability of just B. If independent. Okay, is equal to the probability of A times probability of B. Okay. Okay. There are 7 colored marbles in an urn. Okay, you can okay, you can draw 2 marbles randomly without replacement. The record and colors drawn and record the colors drawn in order. Okay, write each equation in probability notation, then calculate the probability. Okay, so there are 7 colored marbles, 3 red, 4 green. Okay, and you draw the without replacement. That just means without putting them back. Okay, without replacement means without putting them back every time. Okay, you don't put the marbles back once you draw it out. What's the probability of drawing a red ball first, then a green second? So probability of red, then green. Okay, this is the probability sorry, this is the probability of a red and a green. Okay, then a green is equal to the probability of red times the probability of a probability of red, right? Times the probability, what are we doing first? Yeah, we're doing the red ball. Yeah, probability of a green given that I chose the red first. Okay, so what's the probability of the red? Well, that's 3 out of 7. I pull 3 out of 7. What's the probability of the green, given that I've already chosen a red one? Well, that means that instead of 3 red, there are now 2 red and 4 green, which means that I have 4 green out of a total possible of 6. So this is now 4 out of 6. Okay. Multiplying straight across, I get 12 out of 42. Reduce that, they're both divided by 6, that's 2/7. What's the probability of drawing a red, then another red? Okay, so the probability of drawing a red, and then another red. Okay, is the probability of drawing a red times the probability of drawing a red given that I've already drawn a red. Okay. So the probability of drawing a red, again, is just 3 out of 7 on my first draw. Then, what does it do? It goes to 2 reds, so that becomes 2 out of 6. Okay, for the red, given that I've already drawn a red. I don't have 7 in the urn anymore. Okay, in the pot. I have just 6, and I don't have 3 reds anymore. I only have 2. So that's 2 out of 6. So multiplying straight across, okay, we get 6 out of 42, which is 1/7. Okay, there are 7 colored marbles in an urn. 3 are red, 4 are green. You draw 2 marbles randomly with replacement. Now we put it back. Okay, now we're putting it back. What is the probability of drawing a red ball first? Well, the probability of drawing the red first and then the green second. So probability of drawing a red and a green is the probability of drawing a red, okay, times the probability, okay, of drawing a green, because these are independent events now. Okay, why is that? Well, because it doesn't matter if I draw a red or a green before, I'm always going to put the ball back. And so they're independent. So because they're independent, this becomes just the probability of green. Okay, so the probability of red is 3 out of 7 times the probability of green is 4 out of 7. It's not 4 out of 6 this time. It's 4 out of 7 because why? Because I put that ball back. They are independent events. So this becomes 12 out of 49. What's the probability of drawing a red and then another red? Well, again, they're just independent events, so I just multiply the probabilities together. Okay, so this is going to be 3 out of 7 times 3 out of 7, which is 9 out of 49. Okay. So the probability of red and red is just the probability of red times the probability of red. Okay, they're independent events. Draw 3 cards with replacement. It means we put it back, means that they're independent events. Okay, this is independent. What is the probability that all 3 are hearts? Well, what's the probability of getting a heart? Probability of getting a heart is 1 out of 4. So this would be 1 out of 4 times 1 out of 4 times 1 out of 4, which is 1 over 64. Draw 3 cards without replacement. Okay, so each time it's going to go down. The number of cards in the deck are going to go down. What's the probability that all 3 are hearts? Okay, so the first time I draw is 1 out of 4. Okay, or maybe we'll do 13 out of 52. The next time, okay, I draw, there's 1 less heart and 1 less card. So it becomes 12 out of 51. The next time I draw, it's 11 hearts, 1 less heart and 1 less card, because I'm not putting it back into the deck. So I multiply this together. Okay. I can reduce some of these. I can reduce the 13 and the 52 to 1/4. Okay, the 12 and the 50 I can reduce. This becomes 25 and this becomes 6. Okay, the 6 and the 4 I can reduce. This becomes 2 and 3. Okay, And maybe I'll just do that. It's getting kind of messy. So this becomes 3 times 11, which is 33 over 2 times 25 times 51. So this is 50 times 51. Okay, but 51 is divisible by 3. So I can divide this guy by 3 and that guy by 3. So that becomes 11 over 50 times 17. Okay, so 50 times 17 is 850. So this is 11 over 850. That's reduced. Okay, draw 3 cards without replacement. What is the probability the first 2 are kings and the last is a queen? Okay, without putting them back, without replacement here. Okay, to draw a king, it would be 4 out of 52. To draw the next king, it would be 3 out of 51. And to draw the last queen, it's 4 out of 50. Okay, so now all we have to do is kind of reduce this. 4 out of 52 is 1 out of 13, so that becomes that. 3 out of 51, that becomes 1 out of 17. That reduces to that. And 4 out of 50 becomes 2 over 25. Okay, so that reduces. Okay, so if I multiply this bottom together, 13 times 17 times 25 is 5525. So this is 2 over 5525. Okay, example 9. Okay, drug test results out of 1,000 subjects. Okay, subject uses drugs. Okay, we kind of saw this before. Okay, so this is the same one that we had before. So let's see if we can answer some different types of questions here. If 2 out of the 1,000 test subjects are randomly selected, okay, find the probability that they both had false positive tests. 2 out of 1,000 tests are randomly selected. Find the probability that they both had false positives. Okay, so what's the probability of getting a false positive? Okay, well, that's if 2 of the 1,000 test subjects are randomly selected, okay, randomly selected, that they both had a false positive. Well, what's the false positives? The false positives are 90, right? So for the first one, probability, so I want probability of false positive and false positive. Okay, is the probability of getting a false positive times the probability of getting a false positive given false positive. Okay. The probability of getting a false positive is going to be 90 over 1,000. Okay, what's the probability of getting a false positive given that we've already had a false positive? Well, that one false positive is no longer, we already know that somebody got a false positive. That means that it's going to go down to 89 false positives out of 999. Okay. So if I do this on the calculator, I'm going to go 90 divided by 1,000 times 89 divided by 999, and that's about 0.008, approximately 0.008. Okay. Is it likely to randomly select 2 subjects and get that they are both false positive results? Okay, is this result likely? No, not likely. Okay, it's less than 0.05. This is less than 0.05. Okay, so it's not likely. Find the probability that two randomly selected subjects both have a negative test result. Okay, negative. So we have these guys who are negatives. These guys are negative here. Okay. So how many people are negative? Well, there's, for the first negative, I would have 866 people out of 1,000. The second negative would be 865 out of 999. Okay, because once we know somebody's negative, we just pull them out of the pot. Okay, so again, let's just do this on the calculator. Okay, 866 times divided by 866 divided by 1,000 times, oops, not work. 866 divided by 1,000 times 865 divided by 999 is 0.749. Okay, roughly 0.75. Find the probability that a randomly selected person has a positive result given that they are not a drug user. Okay, so find the probability that a randomly selected person has a positive result. So probability that their positive result given that they are not a drug user, given not user. Okay, so by that given, we just want to know that, you know, how many people are not users, right? This is out of the not user. Because of the given, we only are going to focus on this not users. Okay, only out of that. Well, we need to know how many people is that. Well, that's 950 people. If I were to add the 90 and the 860, that would be 150. Or sorry, 950 people. So we want to know what's the probability of a positive test result, 90, out of the non-users. That's 90 out of 950. That's 90 out of 950. Okay. And so that's approximately 0.90 divided by 950. Oops. Clear. 90 divided by 950 is 0.095. 0.095. Okay, about 9.5%. Okay, 5% rule for independence. Okay, if you are sampling, okay, without replacement, and if your sample size is less than 5% of the population, then you can pretend that you are sampling with replacement. Okay, that's cool. Your sample size is less than 5% of the population, means that you have a big population. Okay. Then you can just pretend that it's with replacement. And each trial is independent. Okay. To check, divide the sample size by the population size. Is it less than 5%? Good, then you can be lazy. Thanks. Okay, using the same table from number 9, that's the drug users. Okay. 40 of the subjects are randomly selected. Find the approximate probability that all had negative results. Okay. So the probability of negative is just one person being negative is going to be 866. I think it's at 866. Yeah, it was 866 out of 1,000. Okay. So one person being negative is 866 out of 1,000. Well, but now I want to do 40 of these things. So I'm going to have to multiply this thing 866,000 40 times. Well, how do we multiply something really fast? We use exponents. So this is going to be, okay, the probability of 40 negatives, okay, is going to be 866 over 1,000 to the 40th power. The calculator will do that for us very quickly. Okay, so 866 divided by 1,000. I'm glad we have calculators. Okay, it's 0.866. And now let's raise that to the 40th power. And it's 0.0032, we'll say, 0.0032. Okay, less than 1%. Okay. Okay, number 11. Magazine article reported on Springfield School District magnet school programs. Article examined the impact of applicants' ethnicity and the likelihood of admission. The data are summarized in the table below. Okay. A, find the probability that a randomly chosen student is accepted and white. Accepted and white. It's 316. Okay, so that's 316 out of 1750. Okay, 316 out of 7. Okay, so again, you can plug this into a calculator if you want. But 316 divided by 1750 is 0.181. 0.181. Okay, find the probability that a randomly chosen student is Asian or accepted. Asian or accepted. So we have to look at all the accepteds. We have to look at all of the Asians, and we have to look at the Asian and accepted. Okay, so probability of Asian or accepted. Okay. Won't erase. That's great. Asian or accepted. I'm just going to let C be accepted. Okay. Asian or accepted is the probability of Asian. Okay, plus the probability of accepted minus the probability of both. Okay. So this is going to be the probability of being Asian is 299 out of 1750. Probability of being accepted is 920 out of 1750. And the probability of being Asian and accepted is 120 out of 1750. So 299 plus 920 minus 120. So 299 plus 920 minus 120 is equal to 1099. So this is 1099 over 1750. And we could find a decimal approximation for that if we wanted to. Okay, so 1099 divided by 1750 is 0.628. That's kind of cool. 0.628 comes out nicely. Okay, find the probability that the randomly chosen student is Black given they are accepted. Okay. So there's Black Hispanic, I guess, is given that they are accepted. So we only look at the accepted column here. Okay, that's the given, right? Given isolates that column. Okay, given they are accepted. Okay, isolates that column. So that's going to be 484 over 920. 484 over 920, which is going to be what? Okay, 0.526. Yeah. Okay. Shamil has a flight to catch on Monday morning. Okay, his father will give him a ride to the airport. If it rains, the traffic will be bad, and the probability that he will miss his flight is 0.05. If it doesn't rain, the probability that he will miss his flight is 0.02. The probability that it will rain on Monday is 0.24. What is the probability that Shamil misses his flight? Okay, so let's do a tree diagram for this one. Okay, so there's a couple of things that are happening: rain and missing flights, right? So we want to know, okay, what happens if it rains and what happens if it does not rain? So let's do rain and no rain. Okay, so it says that the probability that it will rain is 0.24. Okay, so this is 0.24. So what's the probability of not raining? Well, it's 1 minus 0.24, which is 0.76. These columns are going to have to add up to 1. Okay. Okay, what's the probability? Okay, it says that if it doesn't rain, or sorry, if it does rain, so it says Shmuel has a, if it rains, then the probability he will miss his flight is 0.05. So if it rains and he misses, okay, that's 0.05 probability. If it rains and he makes it, then that's 0.95. Okay, 1 minus 0.05. Okay, if it doesn't rain, the probability of him missing is 0.02, and the probability of him making his flight is 0.98. Okay, what is the probability that he misses his flight? What is the probability that he misses his flight? Okay, so there are two scenarios here. Okay, there's the rain and misses. So this is, okay, 0.24, the probability that it rains, times the probability that he misses, given that it rains. Okay, so plus the probability of it not raining times the probability that he misses, 0.02. Okay, so we have to add up both scenarios. Okay. Okay, so again, to write this out in, I guess, words, this is the probability of raining and missing plus the probability of no rain and missing. And missing. Let me move this over. Okay, no rain and missing. So let's multiply these together. Okay, 0.24 times 0.05 is 0.012. Okay, oops, wrong calculator. Okay, 0.76 times 0.02. Oops. 0.76 times 0.02 is 0.0152. Okay, and if I add these together, this should be plus 0.012 is 0.0272. 0.0272. That's the total probability. Okay, this is the probability of him missing his flight. Probability of missing. Okay. Okay, 3.3% of the population are infected with a certain disease. Okay. There is a test for the disease. However, that test is not completely accurate. 94% of those who have the disease will test positive. 94% will test positive. However, 4.4 of those who do not have the disease will also test positive. Okay, so those are false positives. What is the probability that any given person will test positive? So we have to talk about the probability of our true positives plus the probability of our false positives. Okay, our true positives plus our false positives here. Okay, so there is a test for the disease. Okay, 94% of those who have the disease will test positive. So how many people have the disease? Well, 3.3% of the population has the disease. So 3.3%, that's 0.0033. 3.3% of the population are infected. Okay, times the 94% accuracy of that test. That gives me a true positive. Okay, plus how many people do not have the disease? Well, if 3.3% have the disease, then 1 minus 0.33 do not have the disease. But of those, 4.4% or 0.044 will come back with a false positive. So 0.033 times 0.94 plus, this is going to be 1 minus 0.033. 1 minus 0.033 is 0.967. Okay. Okay, times 0.044. So now let's put this into our calculator. Okay, 0.033 times 0.94. That's 0.03102. I'm just going to add everything together, round at the end, plus 0.967 times 0.044. Okay, is 0.074, I'll say. So this is 0.074. So about a 7%, about a 7%, 7.4% chance, okay, of getting a positive result. Okay. Positive test result. Okay. Okay, so let's do one last problem here. Okay, Bayes' theorem. Okay. So I don't think we're going to cover the theorem. I'll show you the theorem. Okay, real quick. Okay, so probability of A and B is equal to the probability of A times the probability of B given A all over the probability of B. Okay, so that's Bayes' theorem there. Okay. And again, it just comes to us from the definition of conditional probability. Okay, and so let's use this to try to calculate what's going on here. Okay. So it says there's a 40% probability that Joey will travel to Hawaii. Okay, so probability of Hawaii is 40% chance of going to Hawaii. Okay, which means that there's a probability of him not going to Hawaii of 60%. Okay. If he travels to Hawaii, there's a 90% chance that he'll get sunburned. Okay, so going to Hawaii and getting sunburned is 90%. Not going to Hawaii, or I'll just say staying home, okay, home, and sunburned is 20% chance. Okay, you see Joey after the weekend, and notice he's burned pretty badly, so he got sunburned. What's the probability that he went to Hawaii? Okay. So the probability of him being burned and Hawaii. Let me get rid of the formula. It's kind of, let me just do it intuitively. The probability of him, what's the probability that he went to Hawaii? Okay, so this is the probability that he went to Hawaii given what? Given that we know he's burned. Okay, probability of Hawaii, given that we know he's burned, is equal to the probability that he was burned in Hawaii over the probability of him just being burned. Okay, that's just the probability of him being burned and Hawaii, right? It's conditional probability. Okay, burned in Hawaii. He was burned in over the probability he was burned. Okay, so the probability that he went to Hawaii, given that he is burned, is equal to, okay, the probability is burned in Hawaii. Well, how can I find the probability of him being burned in Hawaii? Well, that's 40% of the 90%. So this is going to be 0.40 of 0.90. Okay. So 40% of the 90%. All over the total probability that he was burned. And that's going to be the probability of him getting burned in Hawaii plus the probability of him being burned at home. That's 60% chance times the 20% chance that he would be burned. So this is how we set up the formula. Burned in Hawaii over the total burned. Okay. So, but the total burned is the burned in Hawaii and the burned at home. So it's those probabilities. So let's multiply this together. This 0.90 times 0.40, 0.36. Stop. 0.40 times 0.90 is 0.36 over 0.36 plus, okay, 0.6 times 0.2 is 0.12. 0.60 times 0.20 is 0.12. 0.12. Okay. Okay, so 0.36 over 0.48, that's 3/4 or 0.75. So there's a 75% chance, 75% chance that Joey was burned in Hawaii, which means that there's a 25% chance that Joey was burned at home. Okay. Okay. Sounds good. Okay, so that's the end of 3.5. The video today went a little long just because I wanted to get through all of chapter 3 in one video. Feel free to take breaks. During the lesson. Break it up. Do 45 minutes, take a break, go get something to eat, something to drink, then come back and then do another 45 minutes. Okay, so yeah. Okay, I'll see you in the next video, and we'll be going into chapter 4.